Welcome to this explainer. Today, we're popping the hood on your computers and smartphones to understand how memory fundamentally operates. Because whether you're seamlessly multitasking for work or trying to squeeze out maximum frames in a heavy video game, there is a fascinating invisible matrix working at lightning speed to make it all happen. It's wild to think about, but why does your ultra-fast, state-of-the-art CPU actually spend most of its time just waiting around? We have processors today that execute billions of instructions every single second, yet they are constantly bottlenecked by one really simple thing: the time it takes to fetch data. No matter how fast the brain of your computer is, it can literally only work as fast as it can get the information it needs. Here's the roadmap for this explainer. We'll start with the workspace analogy, check out the memory speed hierarchy, zoom inside the RAM cell, map out the silicon real estate, and wrap up with the evolution to DDR5. All right, part 1. The workspace analogy, desks and cabinets. Let's picture your computer as a physical office for a second. If your CPU is the worker getting things done, your SSD or hard drive is like a massive filing cabinet sitting way over in the next room. That's your long-term storage. Now, RAM, which we measure in gigabytes for capacity, is your actual physical desk workspace. So when you fire up a heavy game or open, a dozen browser tabs, all that data gets pulled out of the filing cabinet and dumped right onto your desk. It gives your system the volatile short-term space it needs to actually multitask without stuttering or lagging. But here's the thing, sometimes even reaching across the desk takes way too long for our ultra-fast worker, and that is exactly why CPU cache exists. If RAM is your desk, cache is like a sticky note slapped right onto your monitor. Or think of it as a chef's cutting board, literally right under their knife. It holds the absolute most critical data your processor needs at that exact precise nanosecond. Moving on to part 2, the memory speed hierarchy. Nanoseconds matter. Just look at the massive leap in latency we're dealing with here. L1 cache is ridiculously fast, operating in under a single nanosecond, which is just 1 to 4 clock cycles. But then look down at your main RAM at the bottom. We're talking 50 to 100 nanoseconds, or up to 300 cycles. When you're looking at RAM specs, you'll actually see this delay listed as CAS latency, or CL. That just measures how many clock cycles it takes for the RAM to finally respond to a command. And when your CPU is trying to execute billions of commands a second, those little cycle delays seriously bottleneck your overall performance. So why such a massive gap in speed? Honestly, it's just real estate. Closer literally equals faster. Because cache is baked right onto the CPU chip itself, while your RAM is sitting on completely separate modules plugged into the motherboard, that physical distance creates a latency gap you just can't escape. I mean, even when data is traveling at the speed of electricity, having to cross that physical space adds a totally measurable delay. Section 3. Inside the RAM cell, zooming into the silicon. Now you're probably thinking, wait, if cache is so unbelievably fast, why don't we just make all our memory out of it? Well, it boils down to two completely different technologies. We have SRAM, or static RAM, which is that blazing fast tech used for cache. And then we have DRAM, dynamic RAM, which powers your main system memory. This setup perfectly highlights the ultimate engineering trade-off. To store just a single bit of data, a 0 or a 1, SRAM needs a bulky 6-transistor structure. Sure, it never needs to be refreshed and it's lightning fast, but it takes up a ton of physical space and is super expensive to make. DRAM, on the flip side, uses a tiny, honestly quite elegant, single-transistor and single-capacitor design. That lets manufacturers cram billions of bits into a tiny chip for way less money, giving us the massive memory density we expect today. But, of course, that incredible density comes with a catch. DRAM basically stores data as a tiny electrical charge inside a capacitor. Think of it like a really leaky bucket. The crazy part? Just reading that data actually destroys it. It drains the charge right out. Because of this, your computer has to constantly rewrite and refresh that data thousands of times every single second just to keep it alive. That constant refreshing is exactly why we call it dynamic RAM. It's also why RAM is volatile. The exact second you pull the plug and lose power, that bucket empties out and your data is completely gone. Okay, part 4. Silicon real estate, memory controllers. Let's zoom back out for a second and look at the actual physical layout of an Apple M1 chip. You can see a massive chunk of silicon real estate is dedicated purely to memory channels. This is where we see unified memory architectures coming into play. The CPU and the GPU are sharing the exact same pool of low power or LPDR memory. By sharing that pool, the system doesn't have to waste time copying data back and forth between different components. It's a huge efficiency boost. And hey, this is definitely not just an Apple thing. Whether you're looking at a desktop AMD Ryzen 5000 or a massive enterprise-grade IBM Power 10 processor, they all require these incredibly flexible, complex memory controllers built right into the die. These controllers have a really tough job. They have to manage the messy analog interface of the memory modules while simultaneously juggling just insane amounts of data bandwidth. But hardware is only half the story, right? The real conductor orchestrating all of this is your operating system. It allocates the memory blocks and keeps track of all your running processes. And crucially, when your RAM disk gets a little too cluttered, your OS steps in with virtual memory. It seamlessly pages the data you aren't actively using back over to your storage drive to free up room, and then quietly pulls it back into RAM the second you need it again. Finally, Section 5, the evolution to DDR5, faster, denser, smarter. So how exactly has this foundational DRAM architecture managed to keep up with our ever-faster CPUs? Well, look at the jump from DDR3 to DDR4. Instead of just blindly increasing the prefetch capacity, engineers got clever. They divided the DRAM banks into independent groups. That meant each group could separately prefetch and transfer data, which drastically bumped up efficiency without having to completely reinvent the underlying microarchitecture. And then we get to DDR5, where the upgrades are honestly staggering. It brings in dual subchannels on a single stick. This effectively mimics dual-channel performance right out of the gate, giving you massive parallelism and way higher overall bandwidth, which is just the sheer volume of data moving at once. On top of that, frequencies have absolutely skyrocketed. We measure this in megatransfers per second, or MT/s, and DDR5 pushes those rates higher than we've ever seen, all while adding on-die error correction to keep things rock solid. Now, even though the basic one-transistor setup is still at the heart of it all, the tech has really branched out depending on what we need. We've got standard DDR for everyday PCs, ultra-high bandwidth GDDR powering your graphics cards, crazy 3D stacked high-bandwidth memory, and of course, LPDDR. That last one is highly optimized to just sit power, which is why your smartphone battery doesn't completely die after an hour scrolling. When you combine all of these microscopic optimizations, you end up with standard systems today that can easily support a massive 128 gigabytes of total RAM capacity. Just think about that scale for a second. 128 billion individual bytes of data, all sitting right there on your computer's active disk, completely ready to be accessed in mere nanoseconds. Which really leaves us with one fascinating question to wrap up on. As our CPUs keep getting exponentially faster, but the physical space we have to shrink those transistors inevitably starts running out, what radical new memory architecture are we going to invent next? Are we going to see 3D stacking completely take over, or is there an entirely new matrix just waiting to be discovered? Thank you so much for joining me for this explainer. I hope it gave you a totally new perspective on what's really happening inside your devices.